And all right, first type of radio redirection or radio wave redirection I'm going to talk about is called refraction. Refraction, and in this case, they're showing something we call knife edge refraction, is when a radio wave or a light wave, they are the same thing. When frequency gets high enough, it becomes light and the human eye can see it. Light waves are way, way above the microwaves. And we don't even measure them. They're so high, we don't even measure them in frequency anymore. We measure them in a unit called angstroms. Angstroms have a direct relationship to frequency in billions of hertz. But if we use frequency as a general term, they would be such astronomically large numbers, it's mind-boggling. So we started a new unit in angstroms, which are billions of hertz. Okay. So as a radio wave or light comes by an edge, light can become refracted, radio waves can become refracted. They can become focused or bent. Well, focused is caused by bending it. For example, a pinhole camera. You can take a box, put a pinhole in it, put some sort of uh, frosted sheet like plastic on the back end or frosted glass, and the light coming in that little tiny pinhole will get bent and focus on the glass behind it. This is the makings of the original device called a camera obscura. The word camera is the Latin word for room. The word obscura in Latin means dark. Cameras precede film by about 4,000 years. The ancient Romans, the ancient Greeks, even the Egyptians would build these rooms up on the top of very high hills. And they would have one little tiny, tiny little hole in one wall. And on the opposite wall would be a very white wall. And when you went inside this very, very darkened room, they built it in such a way that you could look at the opposite wall, and upside down on the wall, you would see an image of the world outside below. Eventually, artists used this to learn to draw. They would put a piece of paper on it, and they would draw the images that were reflected on the paper. Eventually, cameras obscura were made smaller with mirrors and other devices to straighten the image around, right side around, to take advantage of the other type of way to bend waves, and that's reflecting, which is what a mirror does. And that's the history that eventually became the camera, because by the time they figured out the chemistry in the 1700s to preserve that image, the camera itself was already invented. Even lenses were invented and so on. But refraction bends light. It bends radio waves. So your radio wave can hit a sharp edge and bend ever so slightly, and that will extend where the wave can go. Obviously, if you have a barrier blocking a wave, it stops it. But if it has a sharp edge, it might allow that wave to bend over the edge. But notice something. It does this in what we call quantitative results. It's not a complete bend of everything, it's in segments. So there are going to be spots where it might exist and might not exist. This will describe another phenomenon I'm going to get you a little bit ahead on. When you're driving in a vehicle, you might be receiving a signal that's coming through an indirect path, like being bent. And as you're driving along, it's there, it's gone, it's there, it's gone. And maybe a little further out, it reaches you and it's gone. We call this phenomena, hearing it cutting in, cutting out, picket fencing, because it's like it's getting through the slots of a fence. Sometimes picket fencing is because of the true picket fencing. There's gaps in between buildings, and the buildings are blocking your signal. But at other times, it's because there's also refraction going on, either over the top or around the edge of like a building. Sharper the edge, the more refraction. It's amazing that things like buildings can refract radio waves a little. So a radio wave travels in a straight line. It can get blocked by an object. It can overcome that by refraction. It can also overcome that by reflection. And one of the methods of reflection that we're going to talk about is that it bounces off the upper atmosphere, called the ionosphere. Your book in chapter 4 here talks about the ionosphere. The ionosphere is a portion of the atmosphere somewhere between 30 and 260 miles, as it says in your book, above the Earth. And that zone is very easily ionized, meaning that electrical charge can build there. Once it's charged, it is a certain distance up in the sky that charge seeps down to. Early in the day, it's very high up. As the day goes along, more and more energy builds. It's lower and lower. Because of that, the distance for the wave to hit that part of the atmosphere changes. At night, it's still ionized, but it's a long ways out there because most of the energy is lost in the space in the night sky. And so very, very low frequencies with very long wavelengths will start to reflect back that would not bounce off the ionosphere during the day. That's why late at night, you can sometimes hear around the country AM broadcast stations from all over the place. I can hear Texas stations in Michigan. You can hear Michigan stations up in Maine. You can even hear California stations up in Maine. Right, Preston? It does happen. And this is also what we take advantage of in the evening skip on 160 meters, 80-meter band. As we get into the daylight, the atmosphere gets ionized more and more, and the layers that's being energized with ionized atoms is down deeper, closer to the Earth. And now higher frequencies will bounce off of that. Has to do with wavelength. When I talk about wavelength and ratios and the resonance, this will become clearer. So keep this in mind. We call this phenomena propagation. There are various layers of the ionosphere. The D layer, the E layer, and then the F layer is divided into F1 and F2. The D layer is the closest to the Earth. So imagine D, then go up a little higher is E, then F1, then F2. Depending on whether it's night or day, the intensity of solar radiation is these layers can refract in the E, F1, and F2 layers. Okay? Or they can absorb in the D and E layers. And when they absorb, they kind of do just that. They absorb rather than reflect. That's wasted energy to us most of the time. But remember one thing, neither condition absorbs all the wave energy, nor does it reflect all the wave energy. The atmosphere is kind of like a two-way mirror. When it bounces waves down, it lets some of the waves through, probably the greatest amount, only a small amount comes back. It's the sensitivity of our receivers that really makes this work. All right. There's some pretty good reference here about um, about the ionosphere. But you imagine the signal comes up, bounces down. Now, that's great, but if you look at something, if you know anything about mirrors, a bounce can only have a certain maximum distance. And we can bounce signals all over the world. The question is, how do we get them there? Well, I'm going to tell you. One, if it bounces up, comes down, it can bounce off the earth, go back up, come back down, bounce off the earth, come back down. It can make multiple hops, and that is multiple skip. Okay. It just as it says in your book, radio waves can be completely bent back towards Earth by reflection, and we call this skywave propagation or skip. Mostly we refer to as skip, but the proper term is skywave propagation. It was little understood in the early days of radio. They thought that the radio waves were traveling through the Earth, but it has become something we've come to verify, understand. We have technical means to verify this today. The energy which has been absorbed into the atmosphere to create the conditions for skip are caused by particles leaving the sun. Those particles leave the sun when the sun has high sunspot activity. And the more sunspot activity, the more energy is being put onto the atmosphere. Now, the Earth itself is electromagnetically conductive. So it can also reflect radio waves. Some radio waves you transmit bounce right off the Earth and hop off the Earth a little bit. Earth doesn't do a fantastic job of it directly, but it does occur. You get some skip. Problem is, skipping off the Earth is usually a very low angle. And once it leaves the Earth, it doesn't bounce back. So that portion that we have that directly leaves our antenna and skips off the Earth, unless we specially design antennas to take advantage of it, generally gets reflected straight into space. But it does exist. Okay. And there are times when we take advantage of it. I want to show you this figure 4. Is it the next? Yeah, here it is. Okay, figure 4.3. All right. Signals that are too low in frequency are lost, it says. Well, very, very low frequency signals, they don't reflect anywhere off the atmosphere because there's no point of the atmosphere that's ionized that's high enough to bounce them back. They're too long. Signals that are too short generally do not bounce off the atmosphere because, well, there's no point of energized energy on the Earth, which is ionized, and thank God there isn't, because it would kill us all. We would be constantly walking around getting zapped every time we touched anything, and it would literally kill us all from the energy. So those signals can't bounce back either. And even if they could, they might bounce back like 10 feet away from us. It would be a very short hop. So there's just the right combination of time of day, level of ionized atmosphere, and frequency that gives us the conditions for skip. But there are other skips. Mostly, when we're talking about bouncing off the atmosphere, we're talking about HF frequencies. And that will be something important in the general class licenses. But there are other things that happen. And I'm going to use an earlier picture. Let me leave this. And I want you to be aware of them all. It's covered in your book, but I'm going to go back to a picture that's easy to look at. Let's look at the Earth. Okay, am I showing this? No. Here we go. We look at this picture of the Earth, there's an atmosphere above us. There's the edge of this atmosphere. By the way, anybody have an idea where the space station is related to this? Do you think it's way above this? Because the space station is actually drifting right here at the top of the ionosphere. Um, the ionosphere is very, very thin. It is space in many aspects, but it's still a part of our atmosphere. Okay. But the rest of the atmosphere, well, it has, well, down in this picture, this little gap it shows in here. This is the breathable atmosphere way down here at the bottom. And this is the part we can live in. You get up 6 or 7 miles up, that air is so thin that we need oxygen to reinforce it. We don't have enough air to breathe up there. We get up the ionosphere, we need a spacesuit. It's an atmosphere. It's very, very thin. It's one of the reasons why when it builds up a charge, it builds up a charge that can bounce a signal back because it isn't a real dense layer. That also is why these denser layers cannot charge up enough to provide the signal to bounce back. But what can occur is we can have atmospheric conditions throughout this region down here that will carry radio waves along through it. One of them I'm going to describe to you is called ducting. I'm going to look up a picture for after the break. I'm just giving you a heads up. Ducting is going to be the coolest thing for you in the amateur UHF VHF spectrum. Ducting occurs because of atmospheric conditions, and when it occurs, the radio signal can bounce through a portion of the atmosphere, the lower atmosphere, and travel tremendous distances, hundreds, even thousands of miles. All right, I'm going to get back to lecturing. I was Googling something to make sure I had what I hope I didn't find what I really wanted to show you as a picture because I don't know what I did with it, but I have one that will work and it'll give you a good idea. I'm going to discuss with you two unique forms, excuse me for a minute, two unique forms of propagation for UHF and VHF frequencies. And then I'm going to talk about artificial propagation because we create our own. So I'm going to begin by sharing a screen with you. It's a cute picture. Down below, way below the ionosphere, is a portion of the atmosphere called the troposphere. And you know this portion because you look at it every day. It's where the clouds are. It's where the humidity of the atmosphere is above us. It's where the rain falls from. When water density is high enough up in the troposphere, shorter frequencies can bounce off the water, the moisture, because water is, in a sense, a form of a conductor. It's really not. Pure water is an insulator, but in the atmosphere with other components around it or in the ground with contaminants in it, it becomes a conductor. So when the humidity is just such, UHF and VHF frequencies can bounce off the atmosphere, the lower portion of the atmosphere, but above, of course, where we are, where the clouds are. And this is called tropospheric scatter. It's different than true reflective signals because it is a scatter. You're bouncing off the particles of water. Shorter frequencies bounce off this layer fairly well, but it's a close to the Earth layer. So you're going to get around about a 200-mile, 250-mile maximum range from this. But it does give us a skip. So generally speaking, when we transmit, our signals can go from point A to point B by direct line of sight. It can go longer distances because of some refraction and bend it around objects, over, above, or around. It can scatter off the troposphere. Tropospheric scatter, like all scatter, though, will exhibit some distortion from the scatter, which is why it's different than true reflection. And there's one more, and this one I'm going to draw for you. I'm going to take this fancy color here. I'm going to take a paintbrush. Sometimes what happens is our atmosphere folds over on itself. What happens is normally up here it's colder and down here it's lighter. But sometimes some of the hot gets folded up higher, or some of the cold, depending on the time of year, gets folded down lower. So we get a path, a duct that's, well, it's going to the wrong place. You got a hot layer trapped in between two cold layers, or a cold layer trapped between two hot layers. It becomes what we call an atmospheric duct. And radio waves can enter this, bounce off of this, and even thousands of miles away, come back down. We call this ducting. I have worked Michigan to Maine, Michigan to Florida, Michigan to California, Southern California. The longest paths across the country on 2-meter ducting. 6-meter does it real well. But 6-meter, when it occurs, it's so rare. By the way, we refer to 6-meter as a magic band. It's truly a VHF band, but sometimes it skips so much it acts like it's an HF band. And a lot of hams really love 6 meters because of it. In Europe, they have the 7-meter band, 4 megahertz. We don't have. And that must offer them some really unique experiences too. But I don't know because we don't have it. So we have tropospheric scatter, ducting. We have line of sight propagation. We have diffraction. We also can have reflection, and we actually take advantage of antenna designs. That's how we make beam antennas, to intensify the direction of a signal by reflection. But we also make our own artificial propagation, and we do that with devices like repeaters and satellites. With a repeater, we take in a signal. It goes to a high mounted point, antenna on a high mount generally, which gives great range to that line of sight from, let's say, a mobile or handheld on the ground to the top of a mountain or a very tall building. Trust me, in Michigan, we don't have very many mountains to do this with, but other places do. And now, if that repeater is up on the top of this mountain, for example, if the antenna is up here, that's not a happy face, but anyway. Well, then our signal can come up through it and get repeated back down. And of course, the way we do this is we transmit on one frequency, the repeater receives it. Directly tied to the receiver is a transmitter on another frequency, slightly off in frequency from the frequency that we are transmitting, and it retransmits it on that offset frequency. And since everyone listens on that offset frequency and transmits on the repeater receive frequency, we all hear each other. And we can extend the range of our signal hundreds of miles, hundreds of square miles through repeaters. Most repeaters are set up for 30 to 50-mile range. And the design parameter in the 1970s that we established for ham repeaters, the optimum design, is at least 35 miles of range in all directions that we can possibly offer. And it's with respect to a quarter wave antenna on a mobile running a roughly 15 watts. Today, most repeaters are even more sensitive and more capable than that. So sometimes we get 35 miles out of a handheld. But the original intent was to be mobile communications. And you can sometimes be disappointed with what a handheld might perform. But I can tell you right now, with modern mobile rigs in 2 meters, 440 in a vehicle, even 220, it is not unusual. There are wide area repeaters in Detroit where there are no mountains. There are fantastic repeaters in states with mountains because they put them at the top of mountains. I can work 50 miles north of the city of Detroit, 50 to 50 miles south. So it's not unusual to work 100-mile circle or greater on repeaters. We also can link repeaters either through RF, or nowadays we used to do it through phone lines. Nowadays, through the internet, we can link repeaters so that repeaters can be hooked to other repeaters around the world. So you can be driving along in your car and you're talking on one repeater and it's linked to a repeater in let's say Japan, and you can be talking to a guy going home from work in Japan or walking around his apartment on his handheld in Japan. And yep, we can do all those things. So as technicians, you will utilize all of these techniques, probably use repeaters a lot. You'll use line of sight when you're like at ham swaps and your buddies want to talk to each other, or at some special event that you're helping with. You will use refraction by coincidence. Sometimes some of you might set up to use it intentionally. You will bounce off the troposphere when it occurs. And there's one more. There isn't any room in this drawing, but we have little repeater type devices up in the sky called satellites. And it is possible in ham radio to bounce a signal up off the satellite and back down somewhere else around the world. It doesn't go through the mountain. I'm assuming we go alongside it. I just am out of space here to show anything. Satellites have aboard something called a transponder as a rule. Transponders differ from repeaters. Transponders take a piece of the band, and they retransmit it on another band. So they take a chunk of radio spectrum and they retransmit that on another chunk of radio spectrum, usually completely different bands. On a repeater, I think we covered this in some of the questions last class. On a repeater, we, for example, the standard offset of a 2-meter repeater is 600 kilohertz. So on a repeater, we will transmit on one frequency, and depending upon how and where on the band the repeater is located, the repeater will either transmit 600 kilohertz higher or 600 kilohertz lower. We set in the radio an offset of plus or minus 600 kilohertz, so that our radios transmit on the frequency that the repeater receives, and the repeater transmits on the frequency we're listening to. It works. But in the case of the space station, we have to transmit on a frequency in the case of a satellite, we have to transmit on a frequency that the satellite is receiving in. And then we have to listen on a frequency on another band that it is sending it back out on. There will be, because of the space, some minor delay, so you can actually hear your own voice when you're monitoring. And because the satellite is in motion, there is an effect called the Doppler effect, and the frequency will be constantly changing ever so slightly. So we will always have to slightly, as the satellite crosses across the sky, we're going to have to retune our receive and transmit just ever so slightly every now and then, because it will shift. If you've ever heard a race car zooming along, you know that sound where it goes, as it comes closer, it gets higher and higher in frequency until it reaches this frequency that is the point where it's directly across from you. Then it begins, as it moves away from you, to get lower and lower of frequency. This is called the Doppler shift effect. And it is present in satellite communications because our satellites are not geosynchronous. They're not fixed in one point in space with reference to the Earth. They're orbiting around faster than the Earth is spinning. So they zoom by us. Utilizing ham satellites is usually limited to about 20 minutes per pass at most. But it's kind of fun. It's exciting. And it's a great part of the hobby if you want to get into it. Now, in addition to this, aboard the International Space Station is a true repeater, a ham radio 2-meter 440 repeater. It receives a frequency on 2 meters and transmits back out on 440, if I'm not mistaken. I don't think I have that backwards. And off the top of my head, I don't remember what it is. I'll try to look it up for future classes. You can actually speak to hams on Earth through that repeater. And it works. It's kind of cool. Again, it's limited about 20 minutes. You have to slightly keep retuning a little bit. But once you get the hang of it, it's kind of cool. Okay. So I'm going to cancel this and go back to the book. And any questions on this so far? Sound like exciting stuff? Okay. All right. So things like things that also allow us to skip are things like um, uh, uh, other disturbances to the atmosphere. And they include things like, the northern lights, the auroras, those are charged particles in the sky. You can bounce signals off of them. They will bounce back. They will come back a bit distorted, but it does work. Um, and the reason it comes back distorted is because the aurora, if you've ever seen the northern lights, it's not constant. It's always fluctuating. That's because the ionization of that aurora is fluctuating. And it will allow very, very high frequencies to skip off of it. It's usually short lived. It's kind of cool. It can get you thousands of miles of reflection. You can skip off the trail of a meteor. As a meteor sailing through the sky, this is rather short lived. But as it goes through the sky, it leaves a trail of ionized metal particles. In a sense, it makes a giant reflector. So this is reflection, both of these. And we do take advantage, we can take advantage of it. We call this meteor scatter. It too will be slightly distorted. And it's usually, as described in your book, about uh, 1,000, 1,500 miles. 6 meters works out really, really well for meteor scatter. So does 2 meters, 144 megahertz being 2 meters, and 50 megahertz being roughly 6 meters. I've said to you earlier, and I never want you to forget this. I'm going to give you 3 rules of radio antennas to never, ever, ever forget before I discuss the rest of this. Rule number 1, all amateur radio antennas are a compromise. The reason they're a compromise is because effectively a good antenna, a perfect antenna, only works at one frequency. It's only optimum for one frequency. That frequency is its resonance. And we'll discuss in the class a little further, probably next class, what resonance is in more detail. But an optimum antenna can only operate at one frequency, so all ham radio antennas are compromised antennas. The goal of a transmitting antenna is different from the goal of a receiving antenna. Subsequently, the best receiving antennas are not the best transmitting antennas, and vice versa. The best transmitting antennas are not the best receiving antennas. But as ham radio operators, we can't string out 50,000 antennas to cover 50,000 frequencies, and we can't have another 50,000, so we have one for each frequency that's best for receiving and one for each frequency that's best for transmitting. So it goes back to rule number 1. All ham radio antennas are compromise antennas. Okay? Third, the goal of a transmitting antenna is to best make a signal leave the antenna. The goal of a receiving antenna is to get the most signal to come onto or enter the antenna. They're uniquely different. You see the concepts there? So, ideally, if you had a separate receiver and a separate transmitter antenna, you could get less of a compromise, but because, again, we always want to operate more than one frequency, we don't stay fixed on one frequency all the time, with the exception of maybe where we put repeaters. We tend to put ideal antennas on repeaters or near ideal antennas. All of our antennas are going to be compromised. There's no perfect antenna. There's no perfect goal. And this is why in ham radio, you're going to see people describing all different types of antennas that they use. And each one will tell you theirs is the perfect antenna. Bull crap. All right. I did cover for you guys Ohm's law and it in chapter 2. Ohm's law and the power formula will become very important in the next lecture. Okay. And we're going to jump into resonance and I'm not going to cover this right now, all this right today. I'm going to start on this for next class. But where was it? Here we go. I'm going to talk about impedance again. All right. Because this is going to come important in next week's first lecture. Impedance is a combination of the effects of capacitive reactance, inductive reactance, and resistance. Those three components are always present in an AC signal, and radio waves are AC signals. I want to talk to you about how antennas and radios work. They are dependent upon impedance. Cover this in detail next week. Today, I'm going to give you an overview. A transmitter and a receiver are each half of a giant transformer. Transformer works by winding a coil of wire, feeding an AC signal into one side, which makes a fluctuating AC generated electromagnetic wave. A magnetic field is created when the voltage goes up to the top or peak voltage. In fact, let me see if I can find you a picture to go with that. I'll just keep talking. But anyways, the goal of a no, there's a signal here. Here it is. Okay. In a minute, I'll share a picture with you. But anyways, the goal of an antenna and the purpose of an antenna and the way that it works is exactly like a transformer, as I said. In a transformer, I'm going to do a new share. Okay, let's share screen. This is a waveform. And this waveform is the basis for all radio. It's a sine wave. When the electricity comes out of your wall plug, it is in a wave like this. It's traveling up to a positive value, a peak, traveling down to a minimum value, which is a negative peak, then going back positive towards a positive peak and back down negative towards a negative peak and back and forth. As it does this, it's making a magnetic field spinning in one direction as it's positive. That field collapses when it goes through zero, spins the other way, gets stronger and stronger, and then starts getting weaker and weaker until it gets to zero, collapses again, and spins the other way. In electricity, I believe it's the right-hand rule. It might be the left-hand rule. I'll have to look that up for you for next week, but there's actually a way to figure out which way the magnetic field is spinning around the conductor. Okay? Honestly, it's been so long, I can't remember which rule applies. But basically what the rule says is that you take whichever it is, left hand or right hand, point your thumb in the direction of the current flow, and then the way your fingers would curve around the conductor would determine which way the magnetic field is rotating. When it creates this magnetic field, if there was another conductor right next to it, like these, like this gray line, or I'm sorry, purple line right across here, why then that would create a magnetic field around that wire. Would spin positively, or one rotation, then the other rotation, then back around, back and forth. And that wire would get an induced current. That's how a transformer works. Now, if we, in a transformer, if we put 10 windings of wire on the primary side and 100 windings on the secondary side, 100 windings on the secondary side are going to intersect the same magnetic field. The voltage is going to go up. Current will drop, but because the power remains the same. But that's how we step up and step down voltages. If we spin that transformer around, it will create a step down transformer. And the way that it works is a magnetic field rising, collapsing, going positive, then collapsing to zero, rising back up to positive, in a sense, creates an artificial motion that pushes electrons and pulls electrons back and forth through the wire of the secondary side. And you get a voltage on the secondary side. In a radio, the transmitting antenna is the primary of a giant transformer. The antenna intersects those waves. And so when that wave crosses the antenna, the magnetic field of the wave pushes electrons back and forth because of the fluctuating magnetic field. And that induces a very small but real current and a very small but real voltage, which we amplify and use the tools that I described earlier to reconstruct the radio audio that we put into it, or whatever other intelligence we put into it. This is the basis by which all radio works. The more we can intersect the lines of magnetic flux around the wave that the wave is putting out, and it's all around us, the more efficiently the antenna can receive. On a transmit antenna, we want it to leave at a zero voltage point at the end of the antenna so that we lose the least energy. So we don't want the most lines of flux. We want the point where the antenna vibrates, or the word is resonates, with the frequency of the signal we're transmitting. Optimally, an antenna has a design based upon the wavelength, a transmitting antenna, based upon the wavelength of the signal we're transmitting. If it's not, if we don't cross at zero, if our antenna's length is right in here at the peak, top or minus, plus or minus peak, then there's energy that can't fully dissipate, and it will become reflected back. Some of that energy, at least, will become reflected back. So we often use a device to help us to visualize what's going on, called a standing wave ratio meter, or an SWR meter. It measures the forward power versus the reflected power of the signal leaving a transmitter. We'll discuss that in detail in the classes ahead. I'm giving you foreshadowing. And we're going to discuss antennas, resonance, how this all works in a great deal of detail in the classes ahead. It's going to help you to understand why your antenna for various bands has to be designed a certain way. If you want to operate on lower frequencies, you have to have longer antennas because of the wavelength. And I'm going to describe to you why that occurs in the next few classes, and it will make it all clear.